Hello students, in this video I am going to discuss the questions from the subject Strength of Materials which were asked in MES 2017. Now the first question. The stress developed due to external force in an elastic material is, and now we know that the stress developed in an elastic material is directly proportional to strain, which is Hooke's law, and the constant which we use is the elastic constant which remains constant for the given material, and that is why the correct option for this question is does not depend on elastic constant, that is option 2. Next question. The modulus of elasticity in terms of bulk modulus and modulus of rigidity is. Now we know the relation between Young's modulus and bulk modulus. It is given as E is equal to 3K inside the bracket 1 minus 2 mu. We also know the relation between Young's modulus and modulus of rigidity. It is given as E is equal to 2G inside the bracket 1 plus mu. So if I simplify it further, then E is equal to 3K. Now multiplying each term by 3K, we get this relation. And then if I keep 6 mu k on one side and rest of the terms to the other side, I can get a relation between mu and the remaining terms. Mu is equal to 3k minus E divided by 6k. From this second relation, again I am using the same trick because I want to eliminate mu. So mu I will be getting it as mu is equal to E minus 2g upon 2g. Now equation 1 and equation 2. Left hand sides are equal. I am equating the right hand sides. So 3k minus E divided by 6k is equal to E minus 2g divided by 2g. Cross multiplication will give us this equation. Now thereafter I am collecting the terms containing E on one side, and then I can get the final relation for E as 9 kg divided by 3k plus g. So option 1 is the correct option. Next question. If a solid circular shaft is simultaneously subjected to a torque T and bending moment M, the ratio of maximum bending stress and maximum torsional shearing stress is given by. Now it is a solid shaft, so let it be a solid shaft of diameter d. Now from equation of bending, we have maximum bending stress is equal to M upon I into Y max. M divided by I for solid circular shaft, I is pi by 64 into d raised to 4 into Y max is nothing but the radius, so which is d by 2. So after simplifying, we can get maximum bending stress is equal to 32 m divided by pi d cube. Now from equation of torsion, T by J is equal to tau max divided by R. So tau max is equal to T into R divided by J. T into R is nothing but the outer radius, so it is d by 2 divided by J, which is the polar moment of inertia, pi by 32 into d raised to 4. So simplifying this, I can get T max is equal to 16 times T divided by pi d cube. Now they have asked the ratio of sigma max to tau max. So sigma max divided by tau, that is maximum shear stress, 32 m divided by pi d cube. So this value into this value, so which will be pi d cube divided by 16t, which is 2m divided by t. So the correct option is option 3. Next question. The slenderness ratio of a vertical column of square cross section 2.5 cm sides and 300 cm effective length is. Now the question is related to slenderness ratio, and we know that slenderness ratio is the ratio of effective length to the radius of gyration. So here we will have to work out the radius of gyration. Now let it be that square cross section of sides 2.5 cm each. Its area can be given as 2.5 into 2.5, that is 6.25 cm square. I BD cube divided by 12, but here B and D are same, so it will be 2.5 raised to 4 divided by 12. As such, the radius of gyration is root of I divided by A. Substituting the values of I and A, we are getting it as root of 6.25 divided by 12, that is root of 0.52. We know that root of 0.49 will be equal to 0.7. So root of 0.52, which is slightly greater than 0.49, I am considering it as approximately equal to 0.71. So slenderness ratio is approximately equal to 300 divided by 0.71, and the value, the resulting ratio must be greater than 300 or 360, because 1 upon 0.7 is approximately equal to 1.4. So 1.4, so 1 upon 0.71 will be approximately equal to 1.4. 1.4 into 300 is 420. So the closer value to 420 is 416, and that is why the correct option must be option 4. Next question. Columns of given length, cross section and material have different values of buckling loads for different end conditions. The strongest column is one whose. Now, before going to the solution, let us discuss about the strongest column. Now, strongest column is the column which has the greatest load carrying capacity. Now, the load carrying capacity can be obtained by using the Euler's formula. Pe is equal to pi square EI divided by L effective square. Now, they have said that for given length, cross section and material, means the length has been kept constant, cross section is also constant, the material is same. So if all these terms are kept constant, means pi square EI is, all these terms are constant. So PE must be inversely proportional to effective length, and that is why we will have to check the effective length. Now in this case, in the first case, when one end is fixed and the other end is hinged, effective length is L by root 2, where L is the actual length of the column. When both the ends are hinged, L effective is equal to L. When one end is fixed and other is free, L effective is 2L. And when both the ends are fixed, effective length is L by 2. Now here, Euler's load will be more if effective length is lesser. So it is inversely proportional to the effective length. And that is why out of these four given conditions, the lesser value of effective length should be obtained, and the minimum value of effective length takes place in this case when both the ends are fixed. So when both the ends are fixed, effective length will be lesser. As such, as effective length is at the denominator, its square will have still a less value and the Euler's load will be maximum. So for the given length, given cross section and for the given material, the maximum load carrying capacity, that is strongest case of column, is when both the ends are fixed. So option 4 is the correct option. Next question. A circular shaft was initially subjected to bending moment and then was subjected to torsion. If the magnitude of bending moment is found to be the same as that of the torque, then the ratio of maximum bending stress to shear stress would be. Now in the same question paper, I think it was the third problem in which we have proved that the ratio of maximum bending stress, that is sigma B max divided by maximum shear stress, is equal to 2m divided by T. And that is why here they have said that this bending moment and torque, if they are kept same, then the ratio will be equal to 2, and that is why the correct option is option 3. Next question. A steel bar ABC, so a steel bar ABC has been shown, of uniform cross section 100 mm square, is suspended vertically and loaded as shown in the figure. If the lower end of bar C does not move when loads are applied, now they have asked to neglect the self weight, then the value of force P is, so P is to be obtained. Now I have drawn the free body diagram of AB and BC. So when we draw the free body diagram of BC, 15 kilonewton is acting in downward direction. We know that the entire member is in equilibrium, so BC should also be in equilibrium. 15 is acting downwards, so 15 should act upwards. So this is how the equilibrium of BC can be shown. Now then AB should also be in equilibrium. Total load P is acting over here, out of which 15 kilonewton has been taken by BC, and the remaining will be taken by this member, that is P minus 15, so it is P minus 15 kilonewton. And if the applied or this force is acting is P minus 15, the reaction will also be equal to P minus 15. Now it is said that the lower position C, or this position point C, does not move any either in vertically upward or in downward direction, it remains at the same position. As it remains at the same position, it simply means that whatever is the elongation of BC must be equal to the contraction of AB. So change in length of AB must be equal to change in length of BC. This is what the trick we will have to use. So change in length of AB by using the basic formula PL upon A. P is P minus 15 into L is 50 mm, so I am substituting it over there, is equal to PL upon AE for BC. So when I substitute all the values and if I simplify them, I will be getting P is equal to 24 kilonewton. So key point over here is to draw the free body diagram of these two members correctly. So correct option is option 1, that is 24 kilonewton. Next question, principal stresses at a point in a plane stressed element are sigma x is equal to sigma y, that is equal to 500 newtons per mm square. Normal stress on the plane inclined at 45 degrees to the x axis will be. Now the question is related to the principal stresses and normal stresses. Here I will prefer to use the Mohr circle method. Principal stresses, that is sigma 1 and sigma 2, both are 500 newtons per mm square, so which indicate a point. So both the principal stresses are same, 500 newtons per mm square. So Mohr circle will be a point over here, and as such the normal stress on every plane is going to remain same, which is to be 500 newtons per mm square. Option 2 is the correct option. Next question, the Euler's crippling load for a 2 meter long slender steel rod of a uniform cross section hinged at both ends is 1 kilonewton. The Euler's crippling load for a 1 meter long steel rod of the same cross section and hinged at both the ends will be. Now here they have given two cases. Let it be the case 1. Now in case 1, the length of the slender steel rod is 2 meter. End conditions are both ends hinged. So in case 1, L effective is equal to 2 meter. Case 2. Now the same material is there, L effective is going to be 1 meter. So it is 1 meter over here. Now we know that Euler's load is inversely proportional to square of the effective length. And therefore the Euler's load in case 2, P2 divided by P1 is equal to, now as it is inversely proportional, this ratio will be equal to 2 square divided by 1 square, and which is equal to 4, and that is why the correct option is 4 kilonewton. Next question, a solid shaft of diameter capital D carries a twisting moment that develops maximum shear stress. If the shaft is replaced by a hollow one of outside diameter capital D and inside diameter capital D by 2, then the maximum shear stress will be. Now here there are two cases. In the first case the shaft is solid, so let it be the solid shaft of diameter D. Now in this case, if I use the equation of torsion, T by J is equal to tau max divided by R, then tau max can be obtained as T divided by J. For solid shaft it is pi by 32 into D raised to 4 into R is D by 2. So if I simplify it, I am getting tau max as 16 times T divided by pi D cube. Now in the case 2, it is a hollow shaft with outer diameter capital D, inner diameter capital D by 2. Now tau max can be obtained by using the same formula, that is equation of torsion. Tau max is equal to T divided by pi by 32 D raised to 4, that is outer diameter raised to 4 minus inner diameter raised to 4 into radius. Radius is always the outer radius, so it is D by 2. Now that is equal to 16T divided by pi, inside the bracket it will be D by 2 square raised to 4 will be D raised to 4 divided by 16, and if I simplify it further, I will be getting tau max as 16T divided by pi D cube into 16 by 15. But this term 16T divided by pi D cube is tau max in the first case, and that is why the maximum shear stress in the second case, that is in case of a hollow shaft, is equal to 16 by 15 times the shear stress, maximum shear stress in case of a solid shaft. Now this ratio 16 by 15 is 1.067, and that is why the correct option is option 1.